11.5 Area Between Curves Part 2. From our last lesson, 11.4, we learned that if we have an area enclosed by f of x on top and g of x on the bottom, then the area of the region R is just the integral from a to b of f minus g dx. But what if, here's a second graph, this time f and g are sometimes negative. If the graph is negative, is the area still going to be equal to the integral of f minus g? Is this still correct? The answer is yes. We can still use the same idea, f minus g, to find the area between curves, even if our functions are below 0. Why? Well, it's just like subtracting by a negative number. We know that 3 minus negative 2 is just equal to 3 plus 2, which is equal to 5, right? Well, the area enclosed by the lines y equals 3 and y equals negative 2 between x equals 1 and x equals 4, that's going to be a rectangle. I have the graph right here. The one above 0 I call R. The area below 0 I call S. Okay. So we know the area has to just be the area of R plus the area of S, which is 9 plus 6, which is 15. So it seems like, wait a minute, with areas, I'm always adding positive numbers. So if my functions are negative, how can I subtract them and still get the right answer? Well, let's try this in terms of integrals. Okay. In terms of integral, let's call y equals 3 f of x. So f of x is equal to 3. Let's call g of x negative 2. So y equals negative 2 is going to be g of x. That means that our area is going to be our integral. Let's try it to see if our formula works. We're integrating from 1 to 4. Let's see if f of x minus g of x works. So we're integrating with respect to dx. That's going to be the integral from 1 to 4 of 3, that's f of x, minus g of x, which is negative 2, dx. The key here is we're subtracting a function that is negative, and that becomes positive. We know 3 minus negative 2 is 3 plus 2. So that's the same as 3 plus 2 dx. And to make it even more clear, I'm going to break this apart. That's the area of 1 to 4 of 3 dx. That's the region R on this graph. Plus the integral from 1 to 4 of 2 dx. That's the region S from this graph. So that's why it works. We're really just subtracting by a negative number. If you evaluate integrals, we get 15. That's why even if the function is negative, we can still just do f minus g. Okay. So let's look at an example. This is from AP Test 2006, number 1. Let R be the shaded region bounded by the graph of y equals ln x and the line y equals x minus 2 as shown above. So we see that ln x is always above x minus 2. Let's calculate our integral. So we're integrating from a to b of ln x minus x minus 2 dx. That's the area. We want to figure out where a and b are. What are the limits of integration? Well, when that happens, we know that ln x must be equal to x minus 2. Those are our points of intersection. So we can just go to Wolfram Alpha, just like our last lesson, and have it solve it for us. ln x equals x minus 2, and we get x equals about 0.1586 or 3.1462. Okay, that's what we got. In other words, our integral is really just, the area is really just the integral from 0.1586 to 3.1462, because the first point of intersection is 0.1586 and the second point of intersection, which is right here, is 3.1462. So integrating from 0.1586 to 3.1462 of ln x minus x minus 2 dx. Again, we can just use Wolfram Alpha to integrate this. So we want to integrate ln x minus 2. Remember to put the parentheses around x minus 2 from 0.1586 to 3.1462. And the calculator online gives us 1.949. 1.949. Okay, so that's the area. Next, example 2. This time we're not given the graph. Let f and g be the functions given by f of x is equal to e to the x and g of x is equal to ln x. We want to find the area of the region enclosed by the graphs of f and g between x equals 1/2 and x equals 1. First of all, we want to know which one's on top. Is it going to be f minus g or g minus f? Well, between 1/2 and 1, e to the x is a positive number, and ln of x, ln of like 0.5, ln of 1, like ln of 0.7. Let's use a calculator. ln of 0.75 is negative. They're always negative because they're below e. So ln x is always negative between x equals 0.5 and x equals 1. So f of x is larger than g of x and the entire region. That means that we want to integrate from 0.5 to 1 of f of x minus g of x. It doesn't matter that they're negative. We can subtract negative numbers, which is integral of 0.5 to 1 of e to the x minus ln x dx. Again, we can use Wolfram Alpha to calculate the integral. We're integrating e to the x minus ln x from 0.5 to 1. And we get 1.223 for our answer. So that's the area. Okay. Next. So far, we have always integrated with respect to x. So we use the functions f of x and g of x, and we do the integral times dx. For example, let R be the area enclosed by the graphs f of x equals x and g of x equals x squared. Find R. Well, we know that f of x equals x is always on top of g of x equals x squared. So on top means it's bigger. So that means that the area is nothing new here. It's just the integral of f of x minus g of x dx. And we're integrating from 0 to 1, because that's where they intersect. Yeah. Which is equal to the integral from 0 to 1 of x minus x squared. Again, we can just use Wolfram alpha to calculate our integral. We want to integrate x minus x squared from 0 to 1, and we get 1/6. As we can see right here, is 1/6. But that's not the only way of doing this. What we did in the first question is we said we find these rectangles. Each one has width delta x. Technically, they're trapezoids. Each one has width delta x or dx as they get really small. And the height, well, the height is going to be fx minus gx. But we can also integrate this way. Instead of using vertical rectangles, we can use horizontal rectangles like this. So this time, the rectangle has a height of dy. So the height has to be dy. And the length has to be the function on the right minus the function on the left, because right is larger. The function on the y is g. We're going to express it as a function of y this time. The function of f is on the left. We're still integrating from 0 to 1, because both x and y go from 0 to 1. So what we're going to be doing is we can do the integral from 0 to 1 of g of y minus f of y. It's not always g minus f. It's just because g is to the right of f, so g is larger, so we do g minus f for this one, times dy. And we should get the same answer. But what is g of y and what is f of y? Well, f of x is x, so y equals x. That means x equals y. That means f of y is just equal to y. Next, g of x is x squared. So y equals x squared. That means that y equals the square root of x, which means that g of y is equal to, sorry, I said the wrong thing. Because y equals x squared, we take the square root of both sides. X is the square root of y. So g of y must be the square root of y. SQRT just means square root. Okay. Therefore, our integral of g of y minus f of y from 0 to 1 is equal to the integral from 0 to 1 of square root of y minus y times dy. Okay. Again, we use Wolfram alpha to evaluate the integral. This time we're integrating from square root of y. Again, I use SQRT for square root minus y from 0 to 1. And we get the same answer, 1/6. Why is it the same? Of course, it's the same. It's the same area. It's just that in the first method, we added up the areas of these vertical rectangles. In the second method, we added up all these areas of these tiny horizontal rectangles. We get the same answer. So we can integrate with respect to x or y. So you might ask, why would you ever want to integrate with respect to y? I mean, we have to first change f of x and g of x to f of y and g of y, and that's more work. That's because sometimes it's easier to integrate with respect to y. Here's an example, another MCAS problem. Okay, the functions. Okay, let me take out the answers, so I actually have to do the problem. So the functions f and g are given by f of x is equal to the square root of x, and g of x is equal to 6 minus x. Let R be the region bounded by the x-axis and the graphs of f and g as shown in the figure above. So they gave us a figure. We have two lines. The hard part is that from 0 to 4, x equals 0 to x equals 4, area R is bounded by 0 and f of x. I'm going to call this area R1. Let's use different colors. So this is R1. And from x equals 4 to x equals 6, the area is bounded by 0 and g of x. I'm going to call this area R2. So if we want to calculate the area by integrating with respect to x, we would have to solve two integrals. It's doable, it's just more work. So it's going to be the area is R1 plus R2, which is the integral from 0 to 4 of f of x dx plus the integral from 4 to 6 of g of x dx. Okay, we plug in f of x and g of x, so it's the integral from 0 to 4 of square root of x dx plus the integral from 4 to 6 of 6 minus x dx. Again, we plug this into Wolfram alpha. So we're going to integrate square root of x from 0 to 4. And we get 16 over 3. So the area of R1 is 16 over 3. And then R2, that's integral from 4 to 6. Go back to Wolfram alpha. We're integrating from 4 to 6 of the function 6 minus x. And that area is 2. We could have just used geometry for this one. This is a triangle because 6 minus x and 0 makes a triangle with base 2 and height 2, so the area is 2. 16 over 3 plus 2. 2 is 6 over 3, so it's 22 over 3. That's the area. Okay. But we can integrate with respect to y instead. What happens if we do that? When we do that, we no longer have to do two integrals. Why? Because when we use horizontal rectangles, the area is just bounded by g minus f. From right to left, g minus f. Of course, to integrate with respect to y, we have to find f of y and g of y first. So let's do that. F of x is equal to square root of x. So that means y equals square root of x. So so x equals y squared. We square both sides. In fact, the functions are even easier in terms of y. So f of y is equal to y squared. G of x is equal to 6 minus x. So y equals 6 minus x. So x equals 6 minus y. So g of y is equal to 6 minus y. So our area has to equal. We're integrating from 0 to 2 because y goes from 0 to 2 as seen from our graph of g of y minus f of y dy which is equal to the integral of 0 to 2 of 6 minus y minus y squared dy. Again, we can use Wolfram alpha to calculate our integral. We're integrating 6 minus y squared from 0 to 2. And we get 22 over 3. Again, we get the same answer because we can integrate with respect to x or y. In this case, integrating by y might be easier because it's more direct, just one integral. And really the functions are easier to use. Y squared is probably easier than square root of x. Some students might say, I still like x better. I'm used to using f of x and g of x. Well, in the next few lessons, we're going to start thinking about the volumes of figures made by revolving these graphs. And at that point, we're going to have no choice but to use integration with respect to dy. So you have to get used to it anyway. All right. So again, for this lesson, we learned two things. We learned that to integrate, if we're integrating, even if the graph is below 0, we can still just do f minus g. That's okay. The second thing we learned is we can integrate with respect to y instead of with respect to x, and sometimes that's easier. That's just using horizontal rectangles instead of vertical ones.